Hello and welcome to this recorded e-learning on basic FPGA architecture for the Spartan-6 device family. My name is Frank Nelson. I'll be your instructor for this module. This module introduces the memory resources available in Spartan-6 FPGAs. Please note that there is also available a slice and I/O resources and a clocking resources recording available as well. After completing this module, you will be able to fully utilize the Spartan-6 distributed and block memory resources. You'll also be able to understand the features and limitations of the Spartan-6 dedicated memory controller block, or MCB. You will also be able to use the memory interface generator, the MIG, to build your custom memory controller and design an appropriate interface to your off-chip memory component. This module is important if you're going to be attending the Essentials of FPGA Design course or the Designing for Performance courses. We recommend that you take the time to attend these courses to learn all the critical design considerations you must make when targeting any FPGA device. Every FPGA design needs some memory resources. This is usually accomplished by the use of an on-chip block memory commonly called block RAM, but besides, this Spartan-6 also has other memory resources that we're going to discuss. Block RAM is frequently used for FIFO construction, large data storage, and finite state machine construction, but Xilinx also included distributed memory resources which are often used for shift registers, small data storage, ping-pong buffers, and other small functions. Spartan-6 also includes dedicated and programmable memory controller blocks which allow you to integrate external memory controllers inside of your FPGA. The MCB, or memory controller block, allows you to easily support large data storage applications in which a large off-chip memory component is needed. Just like our soft memory controllers, the MCB is designed to be programmable, so it can support a number of different memory controller standards. This allows the FPGA to be flexible and quickly evolve to meet customer needs of a particular application. All of Xilinx's dedicated memory resources, that is, distributed memory and block memory resources, can be preloaded with data so when the FPGA is programmed, they already contain the memory initialized. And since these resources support both large and small memory construction, they only use the resources necessary for the size of memory you need to build. So they are both fast and flexible. This slide is showing you the memory options available to you with the Spartan-6 FPGA family. There is distributed memory, which is just the LUT reprogrammed to build a little 64-bit memory or a 32-bit shift register. It is very granular and can be grouped to build larger memories very easily when you use the core generator, which is the utility included within the ISE software that is used for all memory construction. Distributed RAM is great for small FIFOs and other common components. On-chip block memory, often called block RAM or BRAM, is a 16 kilobit memory resource that is fast and efficient and ideal for mid-sized data storage. We will talk more about each of these resources as we get further along in the REL. Large memory interfaces or memory controllers are also supported with Spartan-6. Historically, Xilinx has provided access to soft memory controllers which were built with Xilinx's primary logic resources, that is, LUTs and registers. These are still supported with the core generator. Spartan-6, however, has a new dedicated memory controller that allows you to easily build a memory controller that supports several common memory types. This is a very cost-effective solution for applications that require a lot of memory space. Construction of memory controllers is also supported by the MIG. These components are optimized for the IOB resources as well as the MCB resources. As I mentioned, the MCB and the soft memory controllers supported with the MIG are designed to build a number of different types of memory controllers. These can support a number of different I/O standards, single or double data rate, as well as different protocols. This is accomplished with the aid of the Select I/O functionality, which allows direct connection to a range of different I/O standards. This assures high performance and design reliability since the pin assignments are often pre-optimized by Xilinx experts. Distributed RAM is another functionality of the lookup table. Each LUT can be reprogrammed to implement a tiny 64-bit RAM. While most customers do not use this resource, many DSP designers do, so it's a good feature to be aware of. In general, however, you should target the block RAM over the distributed memory. The reason is that block RAM is just a lot bigger. We can always use another LUT for combinatorial logic, but if we fail to use a dedicated resource, such as the block RAM or the DSP slice resources, then it is wasted. The distributed memory is available in about 25% of the slices, which is actually irrelevant since the implementation tools will move your logic around so it can be accessed when needed. It can build single port, dual port, or even multi-port memories when built with a core generator. Likewise, the LUT can be programmed as a 32-bit shift register. Distributed RAM is useful for building coefficient storage, small data buffers, small finite state machines, and small FIFOs. As I mentioned, distributed RAM can be initialized during configuration, so your FPGA can start with your memories preloaded. The write operation of distributed RAM is synchronous and the read operation is asynchronous. The RAM output can be connected to the flip-flops in the same slice to create a synchronous read. Most customers are creating distributed memory with the core generator utility because it will create the necessary input decoder and output multiplexer logic automatically. The two LUTs in a slice, as well as the LUTs in other slices, can be used together to form a larger memory, but this will require extra logic for the input decode logic and the output multiplexer logic to do so. The caveat to this is that the memory built will not be as fast as one built with a block RAM, so most designers will opt for a block RAM implementation. Designers sometimes like to initialize their memory without the use of the coefficient file used when designers build their memory from the core generator. To that end, customers can use the text.io code in VHDL or add an initialization file into their HDL code if they want to infer the distributed memory resource. Spartan-6 block RAM is 18 kilobits of true dual-port memory. This means that each block RAM has independent read and write port widths, and that each port has its own clock and different read and write aspect ratios. Note that if you are used to working with Vertex 5, Spartan-6 block memory does not have embedded ECC logic. Spartan-6 also does not have the dedicated FIFO logic embedded in the silicon like Vertex 5 has. The block RAMs include a configurable aspect ratio functionality, which allows each block RAM port to have a customizable width. This helps the memory lend itself to more applications and ensures efficient use of the block RAM. For example, this means you can write to port A in bytes, plus the parity bit, and then read from port A serially with no access to the parity bits, and also write to port B in 16-bit words, plus 2 parity bits, and then read from port B in 32-bit words plus 4 parity bits. There's simply put quite a bit of flexibility with this configurable aspect ratio that the block RAM has. Spartan-6 block memory also includes a pipeline option for 300 MHz operation. This architecture includes output registers that gives a faster clock rate but does increase the latency. Spartan-6 also has a byte write enable that is helpful to embedded designers that are targeting embedded applications using the Microblaze soft processor core. As I mentioned earlier, you can load the block memory's contents during configuration with the FPGA bit stream. So if you reset the memory while it is running, you only clear the registers, not the contents of the block RAM. It is important for you to not violate the address setup time while the memory is enabled. Leaving the memory enabled while the address setup time is unknown might produce unpredictable results. So leave the memory disabled when you're not writing to the memory. This will also save you some power.